Here's another problem that we can take a look at. We've got a car traveling at 50 kilometers per hour on a flat highway. If the coefficient of friction between the road and the tires on a rainy day is 0.1, what is the minimum stopping distance? And then the second part is on a dry surface where the coefficient of friction is 0.6, what's the minimum stopping distance? Well, if we do part A, we can just plug in numbers and part B will follow right along. So let's go ahead and get part A done. Let's draw a picture here. We've got a road, got a car on that road, and we want to know how long it's going to take to stop. That would be our change in position. And we know a couple of things. We know the initial velocity is 50 kilometers per hour. That's really not going to be that useful to us. We need to convert that to meters per second. So let's go ahead and do that right off the bat. 50 kilometers per 1 hour times there's 1,000 meters per 1 kilometer. So my kilometers cancel. And then I know that there are 60 minutes. Whoops, wrong way. In 1 hour, there are 60 minutes. So my hours are going to cancel. And then in 1 minute, there are 60 seconds. Again, my minutes cancel and I'm left with meters over seconds. So now we can go ahead and take a calculator and calculate this. I've got 50 times 1,000. Enter. Now divided by 60. Hit enter, and then divided by 60 again. Hit enter, and we get 13.9 meters per second. All right, so that's going to be more useful. That is my initial velocity. So V0 is equal to 13.9 meters per second. It's a stopping distance, so that means that V final is going to be equal to 0. This looks like a kinematic equation type problem. I've got a change in position, I've got a V final, I've got a V initial. I've got several choices as far as my equations go. We've got stuff like V final squared is equal to V initial squared plus 2 change in position A. I've got change in position is equal to V initial plus 1/2 AT squared. And I've got V final is equal to V initial plus AT. I don't have time, so I'm thinking that these two equations aren't going to be very useful. Let's take a look at this. I've got V final, I've got V initial. I need a change in position. This is what I'm looking for. And I've got a coefficient of friction, which should help me apply Newton's second law. That would be F net is equal to mass times acceleration. I should be able to apply that to get an acceleration. So let's work that route. Let's go ahead and draw a force diagram for the car. Force diagram would look something like this. I've got force of weight working downward. I've got force of normal working upward. And I've got the force of friction working back and to the left. I don't have a forward force on this. Once I take my foot off the accelerator and hit the brake, the engine stops working the car forward, so all I've got is those brakes, that friction between the road and the car, bringing it to a halt. So I've got my force diagram, evaluating the motion in both the X and the Y direction. In the Y direction, what I'm going to wind up with is that the sum of the forces, well, let's do this. In the X direction, I know I'm going from 13.9 meters per second to 0, so I definitely have an acceleration. So I'm going to need to, in fact, that's what I'm trying to find, so I can utilize my kinematic equation. In the X direction, I've got an acceleration. In the Y direction, my acceleration is equal to 0. So for the y direction, sum of the forces is going to be equal to 0 because my acceleration is 0. So I've got force of normal minus the force of weight. I'm going to go with minus because this is downward, is going to add up to 0. So force normal is equal to the force of the weight. In the x direction, sum of the forces is going to be equal to ma. Problem is I don't have mass. Again, we've seen other problems where we don't need mass. What I can do is either I can go ahead and carry this out and watch mass drop out of the equation, which it will, or I can just say, well, I'm going to make the mass of the car 500 kilograms, just for fun. Mass equal to 500 kilograms, because I already know it's not going to matter. It's just so I can work with some numbers. That means that force of gravity, or force of weight, I should say, force of weight is going to be m times 9.8 meters per second squared, which is going to be 500 times 9.8, which is going to be 4,900 newtons. And that means that in the x direction, my frictional force is going to be equal to, well, that makes this 4,900 also because Fn is equal to Fg. Force of friction is going to be equal to 500 kilograms times the acceleration, which I don't know. So I need friction, but I've got coefficient of friction is equal to 0.1, which is equal to force of friction over force of normal. Well, my normal force is 4,900, so that means the force of friction is going to be equal to 0.1 times 4,900, which is going to be equal to, let's go with 4,900 newtons, which is going to be equal to 490 newtons. So now I can go ahead and say that force of friction, now keep in mind this is going to be negative. Keep in mind this is going to be negative because this is pointed to the left. So I'm going to have negative, it's from this, 490 newtons is going to be equal to 500 kilograms times acceleration. The acceleration is going to be equal to 490 newtons, this is negative, divided by 500 kilograms, which is going to be 490 divided by 500 is 0.98 meters per second squared, and that's negative. I almost lost my negative sign there. So now I'm ready to go ahead and do my kinematic equation in order to get my result here. So I've got V final squared, which is 0, squared, is equal to V initial squared, 13.9 meters per second, and that's going to be squared, plus 2 times the change in position, which I'm looking for, times negative, I got to move this, it's in my way, what did I say, 4,900? $4,900 newtons. All right, So times negative 0.98 meters per second squared. This goes over to the other side, so I get a, oh, let's go ahead and get a number for that. 13.9 squared is 193.2. So I got 0 is equal to 193.2 meters squared per second squared plus 2 change in position times negative 0.98 meters per second squared. I should just multiply out. Never mind. Oh well. So I get negative 193.2 meters squared per second squared is going to be equal to negative 2 times 9.98 meters per second squared times change in position. I just kind of rearranged the order a little bit so I wouldn't get lost there. I'll go ahead and finish this up down here. So I'm going to have 193.2. We'll deal with units in a second here. Divided by negative 2 times 0.98 is equal to change in position. So that's going to be equal to, let's go ahead and grab a calculator. It's going to be 193 divided by, whoops, 0.2 divided by 2, hit enter, divided by 0.98, hit enter. Looking at about 98.5, 98.6 meters. 98.6 meters. I know that change in position is going to be in meters. Let's go ahead and take a look at the units just for fun. Here's my, hard divisor between my numerator and denominator. On the top, I had meters squared per second squared. It's from here, and on the bottom I would have had meters per second squared. So the bottom of the top goes to the bottom of the bottom goes to the top, and we wind up with meters squared times second squared, because these come up here and these go down here. So I get meters times second squared. Look at that. Those guys cancel out. That cancels with that. I'm left with meters. So the units do work. Again, I didn't need the mass because what would happen is the mass just drops out. So I can put whatever mass I want in here and it'll work. Now I could go through this for 0.6. I'm not going to go through all those calculations. All that would happen is right here at this point, this let's put something bright, able to see here. Yeah, go with that. This right here would go in here, and it would change this number, which would then be used here, and it would change this, and then that would change this, and you would just carry that on through. Again, we didn't need the mass because the mass dropped